So today I'm going to talk about the long-time dynamics and nonlinear inviscid damping for 2D Euler equation. And this is joint work with Alex Ionescu, who is in the audience. Oops. Okay. So we consider the two-dimensional Euler equation in the vorticity formulation. So you have the partial T omega plus U dot gradient omega is equal to 0, and U is given through the Beer-Savart law. So U is equal to the gradient nebula perpendicular Laplacian inverse of omega, which is exactly this. So omega is transported by the velocity field, which is generated by the vorticity field. It's a nonlinear equation. It is well known that smooth solutions for this equation remain smooth and exist globally in time, because notice that we are in 2D instead of 3D. 3D, of course, it's different. We're in 2D. Solutions are global. So there's no issue with regularity for this equation, but the long-time behavior of smooth solutions is hard to understand because there's no global relaxation mechanism. There's no Laplacian, no decay, no explicit decay, and no dispersion, and those well-known relaxation mechanisms are absent. So as a result, there are very few results on the precise dynamics of general solutions. I mentioned two here. So one is the renowned result by Arnold on stability, which gives nonlinear stability around some steady states, but there's no description on the precise dynamic of the solution. And there's also a result by Lin and Zhang, and they construct the unstable manifold when your steady state is not stable. So you have some unstable direction, so then you have finite dimensional solutions which you can control, and they exponentially converge back to the steady states when you run time backwards. But in numerical simulations, especially if you have numerical simulations of slightly viscous, viscosity very small, two-dimensional Navier-Stokes flow. But actually, somehow, even if you numerically simulate the 2D Euler, but sometimes it is difficult to distinguish the two because very often the numerical scheme could involve some cutoff in frequency. But in any case, at least for slightly viscous two-dimensional flows, one often observes two very prominent processes. The first one is the so-called axisymmetrization of vortices. The second one is the merging of same sign vortices. So these are, I think these are two most important processes for 2D Euler. And they can, if we understand these things, we would go a long way in explaining the 2D turbulence, which is much more structured than 3D turbulence. So the mechanism for the first process, which is axisymmetrization, that's exactly, the mechanism is exactly nonlinear inviscid damping, which we will talk about. The second one, the merging of vortices, that's truly non-perturbative, and we have little understanding of that. So I have a little movie. This is done by Theodore Drivas, and I have permission to play it here. Thanks to Theodore. So you see here is initially there's some pretty chaotic distribution of vorticity where the blue is negative, the red is positive, and you clearly see that it simplifies, right? The distribution becomes simpler. You have these vortices and they will merge, and this you see that if the large vortex get into contact with the smaller one, it simply axisymmetrize it. It's like a machine destroying the small structures. And in the end, you will only have like two of them left. So basically two processes. If the bigger one kind of run into any small patch of vortices, we just eat it up. Or even when the two vortices, if they are same sign, are getting close enough, they will actually merge together, but that's much more complicated. There's a change of structure involved. So I think the movie plays a little further, but I think it's the phenomenon is pretty clear now because it's a periodic domain. It's a square periodic domain. So these two guys are actually the same, right? Now you only have two left because it's periodic. So yeah, now it's very clear. You have only two. So those are quite robust phenomena. And if you search free decaying two-dimensional turbulence on YouTube, you find many more videos of this type. But this one is probably more accurate. Okay. But those things, I mean, at least the merging is hard. So we will talk about the axiomatization, which is close, I mean, not nonlinear inviscid damping, which is closely related to the axiomatization. So we consider the perturbative regimes near steady states. So there are many steady states for 2D Euler. There are many infinite dimension, finite codimensional manifold of steady states. But perhaps the most important ones are shear flows or vortices. And actually the analysis of the two share many similarities. Not completely the same, but they share many similarities. So the stability of these coherent structures is a classic topic, and it's already studied by the pioneers like Kelvin, Rayleigh, or Helmholtz, among many others. And the focus was on modal stability, to just say if it's exponentially stable. And then linear, more recently, linear asymptotic stability and nonlinear asymptotic stability. And recently, there have been, maybe last decade or so, quite a lot of progress on both linear and nonlinear asymptotic stability. So to begin with, for the vortex symmetrization problem, let me make it very clear that the general case is still open. Okay, the nonlinear problem, it's still open. We have some partial results. The first one is due to Bezoshin, Couette, and Rico on a linearized flow, which basically prove that for the vortex symmetrization, at least on a linearized level, the vortex symmetrization happens. But for the nonlinear problem, we only have the result when the vortex is not arbitrary. The vorticity field is not arbitrarily distributed, but rather just a point vortex. So you have a point vortex in the center, and then you perturb that. So to state our result on the point vortices, so we consider solutions to 2D Euler, which is written as some coefficient kappa, which is non-zero. Okay, it has to be non-zero. Kappa Dirac mass centered at some point pt plus a perturbation. So pt will actually move. So pt is the position of the Dirac mass. I heard a sound. Is there a question? Okay. So the perturbed, so omega is a perturbation. So the perturbed equation is the following. You have partial omega plus this term plus the u dot gray omega is equal to 0. The extra term is the velocity field generated by the Dirac mass. Okay, and then the position pt of the Dirac mass will also change due to the external velocity field, and it's driven by so p prime t is exactly the velocity field generated by the external vorticity. So the main simplification of the background flow being given by the Dirac mass is that the Dirac mass has no inner structure. Okay, it's just a point, so it's no inner structure. So it will not, if you have a general vorticity like vortex, which is a radial function, then it has some, it itself could deform, and that we do not quite understand fully yet. So this equation looks like it's more complicated than Euler because you have one extra term. But in fact, this extra term is what makes things converge. Okay, it's the stabilizing mechanism here. So this equation can be rigorously derived if the position of the Dirac mass is outside of the support. Because the Dirac mass is pretty singular for the 2D Euler, one might worry about the validity of this equation, but there's no problem as long as PT is outside of omega t. And moreover, this support condition is propagated dynamically by the flow as a consequence of the proof of stability. So we proved with Alex Ionescu that small, Jeffrey smooth, and compactly supported perturbation symmetries around the point vertex. And the point vertex will move, but it will stabilize very, very rapidly as time goes to infinity. So the position of the Dirac mass immediately stabilize, and the perturbation initially may be localized in one corner, but then it will immediately symmetrize, very quickly symmetrize to, not so quickly, but it will symmetrize around the point vertex. Just like we see in the video, except now at the center, you instead of a general vorticity, a general vortex, you have a point vertex. So more precisely, if your initial data is small, is Jeffrey norm, the Jeffrey 2 norm. So okay, it's not a Sobolev norm, it's a Jeffrey norm. So the weight is exponential, but the power is half here because it's Jeffrey 2. And then you have a smooth solution, omega and p. So p is the position of the Dirac mass. So this omega p, that gives the complete system. It has a unique solution, omega p, and the p will always stay outside of omega, and the p stabilizes to p infinity very rapidly, and omega converges weakly to a final function, which is smooth. So the final profile, which is a radial function and smooth. That gives the description, the first step in the nonlinear axisymmetrization. I will not actually discuss the proof of this result because it's kind of contained in some sense. It's contained in it's contained in the proof of the following result. So next we consider the general shear flow case. So very recently there's some, this slide is probably done a few months ago. At that time it was very recent, but now it's not so recent. But recently there are some Braxels. We now have a much better understanding. So now we consider perturbation around shear flows, okay, instead of vortices. So now we write the velocity field and the vorticity field as by0 plus u and the minus b prime plus omega. So by0, so you have this is a parallel flow. You see that it's a parallel flow. The second component, the perpendicular component of the velocity field is equal to 0. And you only have the horizontal velocity, and the velocity only depends on y. Now, written in this form, the perturbation u and omega satisfy the following Euler equation. You have partial t omega plus by partial x omega minus b double prime y partial x psi plus u dot omega is equal to 0. Again, in addition to the ordinary term u dot gradient omega, you have two extra terms. Similar to the vortex case, these two terms will help us, especially the second term, it will help us stabilize the flow. And the stream function, of course, can be recovered solving the Laplacian equation, and the velocity field is again given by the Pierre-Savarin law. So since we work in perturbative regimes, we assume that the stream function and the vorticity the perturbations will be always small, and we want to study the behavior as time goes to infinity. So we need some notation and conditions. So let's first recall the Jeffrey space. We work in the domain where x is periodic with the period 2 pi, and the y y will be in the interval, in a finite interval, but now the Jeffrey space is defined on the whole space. You take for function f, you take the Fourier transform in both x and y, and then you multiply this exponential weight, where the s is from 0 to 1, and s being 1 is the analytic function. For us, s will be taken as a half. So we assume we have to have some assumption on the background flow. Basically, the background flow is smooth. It's monotone, so the b prime is bounded away from 0. It's smooth, and importantly, we have to assume that the shear flow, background shear flow is linear near the boundary. So this is an important assumption. And then we know that if we do not assume that, the theorem as we proved will not be true. Actually, there's another condition, that is the linearized operator around the background flow is spectrally stable. So there's no discrete eigenvalues. Because if you have discrete eigenvalues, likely you will have some other things going on. So you will not have linear stability. So that's a necessary condition as well. And then we prove that if your initial vorticity is supported away from the boundary and small in the Jeffrey 2 norm, then of course the 2D Euler has a smooth, globally exists smooth solution, but we have the following very precise, but in addition we have the following very precise conclusions. The first one is that the vorticity will be supported away from the boundary for all time. And this is a very important condition for the analysis, because the boundary effect for the 2D Euler, okay, even for the 2D Euler, the boundary effect is very important if you want to study precise dynamic. I mean, we all know that for Navier-Stokes, the boundary effect is very important, but in fact, for the Euler, it's also very important. And the most important conclusion, the second one, the renormalized vorticity has uniformly regular profile. We know that the 2D Euler is a transport equation. So in general, the vorticity, especially in this case, which can be shown rigorously, that the vorticity field will become rough and rough because it's transported around, it's mixed around. But in this case, it is possible to make a transformation, change of coordinate. So instead of looking at omega in tx coordinate, you look at in this coordinate. Okay, x plus tby plus phi ty. So phi is given explicitly in terms of flow. And if you look at it in this coordinate, then the vorticity is very regular. It's actually very regular and converge to a final profile with a specific rate. So you see that the change of coordinates is given explicitly as the flow, from the flow. And the third conclusion is the return of velocity fields to shear flow. So the velocity field initially could be quite complicated, but in the end, the perpendicular direction component will go to 0 with 1 over t square rate, and the horizontal direction will converge to a final profile of u infinity y with specific rate. So that is saying that if you have initially have a perturbation, then in the end it will just become another shear flow. So I have a few remarks on the result. So the first one is that the assumption on the compact support is necessary to avoid boundary effects. So this you can already see when b double prime is completely 0 and omega naught is not compactly supported away from the boundary. You can see that the boundary terms, it's like you integrate a Green's function against the oscillatory function. You will pick up some boundary terms which oscillate differently than the term from the singularity of the Green's function, right? If you integrate a Green's function against the oscillatory function, you will have oscillatory effects, but the non-oscillatory effect should be the one given by the singularity of the Green's function. But if your oscillatory function is not compactly supported, you will pick up two additional boundary terms, which oscillate with a different phase. And then how would that affect the final dynamic? That's not completely understood, but we know that as it stands, the theorem as it stated, it will not work. Of course, in perturbative business, it's very hard to say that absolutely nothing will work, because you can always try something else, maybe a modified profile or something like that. So it will not. I will not say that nothing will work, but the theorem as it is stated is not going to work. So we have a condition in addition to the background flow By being linear near the boundary, we also assume that there's no discrete eigenvalues for the linearized flow. This can be satisfied if, for example, I mean, there are many such flows, but the one particular case would be when you impose some sort of bound on the third derivative. In that case, you will not have any discrete eigenvalue. The Jeffrey assumption is also likely sharp, and this has been demonstrated by Masmodi, who considered only initial perturbation, which is slightly worse than Jeffrey 2, and then the theorem, they show that the theorem fails. And a more definitive counterexample by Lin and Zheng in low regularity Sobolev space. But the mechanism is different. For the Lin and Zheng example, basically, because you perturb things in such a rough space, you destroy the linear structure. Okay, it's a really bad situation. There's enough room because you perturb in such a rough space. There's enough room to actually create an eigenvalue on the linear level. So it's not about the nonlinearity in some sense. So at the qualitative level, our main conclusion shows that the vorticity omega converges weakly to a final function f infinity. And this is consistent with a far-reaching conjecture regarding the long-term behavior of the 2D Euler equation, which says that for generic solutions, the vorticity field converges as t goes to infinity weakly but not strongly in L2, local to some steady state. It's not clear how to prove such a conjecture, of course. But the results we have so far are consistent. Lastly, let me mention that Masmodi and William Zhao recently also have a different, they also have a proof of the result, which is different from this. So below, I will outline some main ingredients in the proof. So there are three main components, basically. So the first one is analysis of the linear evolution in Jeffrey space, because the nonlinear analysis requires Jeffrey regularity, so we have to analyze the linear flow in this space. The second one is nonlinear analysis built on the ideas of changing variables and energy functionals. The third one is somehow to combine the two, which turned out to be quite non-trivial for this problem because the linear analysis and nonlinear analysis are a little bit different. Oh, sorry, I have a misspelling for estimates. So let us look at firstly the linearized flow. The linearized flow, because the shear flow is independent of x, so the linearized flow actually decouple in the x variable. So we can take a Fourier transform in x, and in the Fourier mode k of x, the flow decouples. So there's nothing on the linearized level, at least. This becomes a evolution equation only in y for each k. So you see that omega partial omega plus k plus ik by omega k minus another term is equal to 0, and you see that omega k from regular initial data omega k will become oscillator. We'll pick up this oscillatory factor, and then the decay mechanism, I mean stream function, is recovered from this elliptic equation. Then you see the decay mechanism clearly by, at least in the case when b double prime is equal to 0, by integrating the vorticity field against the Green's function. So that gives you a stream function, and you see that okay, you have the Green's function integrating against this oscillatory function, and so you have oscillation. So you can have decay, right? Because if you integration by part, integrate by parts in z, you get 1 over t. And you can do this twice, but not more than twice, because the second derivative in z of the Green's function already picks up Dirac mass, so that already gives a main term. And you also see the boundary effect from this formula, because if your omega is not supported away from 0 and 1, you will have some boundary terms. which decay in a different manner. Oh, sorry, oscillating in a different manner. So we denote the linearized operator. I mean, this is true for in the case when b double prime is equal to 0. If b double prime is not equal to 0, the non-local term in the equation, the linearized flow, will become important, and we have to understand how that affects the evolution. And that turned out to be a slight non-trivial problem. So we denote the linearized operator LK as the following. So LKF is BYF plus B double prime of this expression. So that's simply the string function associated with F. Then the linearized evolution can be written abstractly as positive omega k plus ik lk omega k is equal to 0. And an important result by Dongyi Wei, Zhifei Zhang, and Weiren Zhao is that they proved the linear inviscid damping. So the same damping as in the Couette case, the string function decays like 1 over t squared. The first derivative in x decays like 1 over t squared, but the first derivative in y decays like 1 over t. I mean, this can be read off from the formula if you have Couette flow, and you can see also the difference between the derivative in x and derivative in y, because derivative in x just translates to multiply ik. That does not change the decay in time, but derivative in y, that changes because the derivative in y will decrease the differentiability of the Green's function. Then you can only integrate by parts once, so that you only get 1 over t. So let me also mention earlier works by Stepin, Christian Zillinger, and some later some also alternative proofs, not exactly the same result, by Grenier, Nguyen, Rosset, and Soffer, and myself. But unfortunately, linear estimates, as stated above, are not sufficient for nonlinear applications. So this is like what they prove are like dispersive estimates. So you try decay in decay in frequency variable for decay in time. But it turns out we would need more precise bounds on the profiles instead of just like a magnitude type of control. So this can be seen again very clearly from the Couette case in when by is equal to y, where in which case the linearized flow simplifies to a simple transport equation, and you can solve it explicitly. So omega is given in this formula. And if you take the Fourier transform in both x and y, you get a formula for the string function like this, where omega naught tilde is the Fourier transform of the initial data. Now, of course, this guy is not uniformly smooth because in time, because if you imagine t is very large, this can only have uniform decay like 1 over k squared t squared. So that's not very regular. I mean, the regularity depends on t. So, but you can remedy that by changing by a changing variable, and then if you look at your string function in the new coordinate like this, and then you can take the Fourier transform and get this formula. And now everything is very smooth, uniformly in time. But you see that if you really want to, I mean, also you have a decay because when you see that omega naught, if your omega naught is very smooth, then omega naught Fourier transform omega naught is fast decaying psi. You basically can view psi as of order 1, and then the factor below will give you 1 over t squared kind of decay. But you see that one should not try to convert this into a pure power like decay, because if you want to bound the 1 over this quantity by 1 over t squared, you would have to somehow couple it with psi squared, and then you lose 2 derivatives at least to recover the 1 over t squared decay. But in considering nonlinear analysis, that's too much to sacrifice, because in the nonlinear analysis there's no room to it's a transport equation. There's no gain of regularity anywhere. You can't lose any derivatives at the linear level. So for the linear analysis to be successful, in order to apply for nonlinear analysis, we have to keep track of this factor instead of convert it into a like 1 over t squared type of power type decay. So then it turns out we can do that in some coordinate, like v is by, z as x minus tv. We again write the similar profile in that variable for the stream function, and we can prove that in that variable you do have a similar estimate, where you can see this decay factor, which depend on frequency and time. So the key point of the proof, I think I have to speed up a little bit. So the key point of proof is to analyze the spectral measure in Jeffrey space. So using spectral, it's a linear problem. You can always write down a spectral representation in terms of spectral density. These two functions are the spectral density function. And these satisfy the following boundary value problem for the kind of ODE problem, like this. The key feature of this problem is that there's a singularity, because you see that there's this factor here. When y is equal to y0, this coefficient will simply be singular. So you see that at most, you can control the stream function up to second derivatives, right? The second derivative will already produce a Dirac mass-like singularity, but somehow the stream function is completely smooth, right? I think that was initially the obstacle people find a little confusing, that somehow your stream function are very singular, but when you integrate everything, it becomes smooth. It turns out the key point is to capture the singularity, the structure of singularity in a very precise way. And the key point is that you can, if you make a chaining variable setting v as by, w as by naught, the singularity will be transformed to 1 over v minus w. Okay, that's still singular in both v and w, but then if you shift v to v plus w, then the singularity becomes 1 over w. 1 over v. In that case, if you make this chaining variable, it turns out this function will be completely regular in w. So that's kind of the key structure you have to, the key singularity structure one has to capture in order to prove smoothness in regular Jeffrey smoothness of the stream function. Okay, so that's all I want to discuss about the linear flow. For the nonlinear analysis, at least so for the initial breakthrough is for the Couette case, where the linear problem is kind of easy. The main difficulty are the nonlinear problem, the nonlinearity, and the breakthrough is due to Bedrosian and Masmoudi in the whole space T times R. And Alex and I considered the case when finite channel to study finite energy solutions. So Bedrosian and Masmoudi introduced two important ideas. The first one is the so-called nonlinearly adapted coordinates. So as we have already seen, that vorticity is transported around. So if you want to obtain uniform in time estimates, one has to cancel the transporting x. So by changing a variable, so they make this changing variable, and in the new coordinate, the Euler equation becomes this. It looks like a little more complicated actually, but the key point is that the velocity field, all the velocity field now transporting f are now decaying in quadratic fashion, like 1 over t squared. So all the velocity field now decays in an integrable fashion. So you can hope to control f uniformly in time. And of course, the stream function phi, the renormalized stream function in phi also still satisfy this elliptic equation. And in this one, because everything is close to Couette, in fact, we have good knowledge of v prime, the coefficients, and v dot, and so v primes of order 1, v double prime is small, v dot is very small and decays fast. Not very fast, 1 over t squared. So we can consider the following simplifying model, which is partial tf minus this velocity field partial zf is equal to 0, and this phi is given as this solution to the elliptic equation. And actually, this is a self-contained system. One can study this to gain some insight for the nonlinear analysis. So then the main objective is to control the uniform in time regularity of the function f. The major issue in this case is that the velocity field has a derivative in v. Okay, the velocity field is given by derivative in v of phi, but phi satisfies the elliptic equation where you recover derivative not in v, but in v minus partial v minus t partial z. So you do not really recover a derivative in v, but you recover this factor. So that's the mismatch. That's a mismatch. which translate in the free variable as a large factor, xi, 1t is equal to xi over k. And in order to handle this difficulty, we use some energy functional. You kind of measure the profile f using the energy functional with some sort of weight which you design. And the key point is that, I mean, that's the key original idea of Bezushi-Masmoudi, is to design a weight which is imbalanced. I don't have much time to discuss this, but the key thing is that if you change a parameter in the weight at a specific place, then the weight changes a lot, and that turned out to be very helpful to deal with this large factor. Okay, so that's a nonlinear analysis for the Couette case. For the general shear flow case, we can make, to begin with, we can make the same kind of changing variable, try to cancel the transportation effect. So in the new coordinate, we have a bunch of functions. The man profile for the vorticity, profile for the stream function, the coefficient due to the changing variable, many coefficients, and the background flow, because in the new coordinate, actually the background flow also starts flowing, starts being time dependent. So, but in any case, so there are many profiles that we need to control that actually complicate the analysis. But the man profile to control is F. Okay, that's the key thing. So F satisfies the following evolution equation. You have these two, the nonlinear term, which are as in the same as in the Couette case, but you have one extra term b double prime partial z phi. Now in the Couette case, b double prime is 0, so you don't have that. But in the general shear flow case, b double prime may not be 0. In fact, it's not even small. So this is not perturbative. The rest of the terms are perturbative, and this is the key additional difficulty to handle. So now we have a situation where the nonlinearity, the pure nonlinearity can be completely understood. The pure linear flow can also be completely understood. Now somehow we have to combine the two, and the difficulty is that the methods for understanding those two processes are very different, and somehow we have to find a way to kind of combine the two analyses. So the idea is to try to decouple the linear and nonlinear dynamics. So to do that, we introduce an auxiliary profile, which takes into account the linear effect and evolves in a perturbative fashion as follows. So we define f star as f minus the integral of this quantity. This quantity is inspired by the linear term here, right? You see that f, basically you are integrating the first two terms, right? And set it as the auxiliary profile. The first two terms you remember, you set as a kind of the auxiliary profile, but we have to make some crucial changes in order to later on connect with the linear problem. So in this term, beta prime is time dependent, and phi solve this elliptic equation also with time dependent coefficient. But I mean the evolution of the coefficients will also depend on the full solution. So if you integrate the term completely, you will lose touch with the linear analysis. So instead, we freeze the coefficient. We freeze the coefficient, and also we impose that the stream function solved. We also impose freeze the coefficient in the elliptic equation. Okay. The idea behind it is that we somehow all these guys are kind of a time. They all depend on time, but they depend on time in a very small way, right? They only kind of basically you can view it as a bulk function, which is very smooth, plus a small nonlinear perturbation. So the difficulty with treating this term is not the small nonlinear perturbation, because now we can throw it away in the nonlinearity. The difficulty is the bulk smooth term. So this exactly captures the bulk smooth term. Sorry. Okay. So now you can view that this is some sort of this is the kind of bounded transformation for f, because this phi prime is solved from f. So this is linearly depending on f, and this is f. So f star is a bounded transformation of f, and in addition, f star already takes into account the linear evolution. So f star evolves in a perturbative fashion. Okay, there are actually some difficulties. I don't have time to discuss in the details, but f star, there are modulo some additional difficulties. F star can be controlled using perturbative techniques. Now, you can control f star. How about f? Because f is the man profile that we have to control. So notice that f star is obtained from f through this bounded linear transformation. So our task is to kind of invert this transformation, so to speak. And that turns out that can be done using the linear analysis we had before. So if we define the string function associated with the auxiliary profile, this is a string function associated with the auxiliary profile. Because we have already obtained very good estimates on f star, this phi star also enjoys good estimates. So that's also known. So we want to, now we set g as f minus f star, phi as phi prime minus phi star. So if we look at this, so we have phi prime, which is a string function associated with f. Then we define the string function associated with f star, keeping in mind that f star we have already controlled. So we know everything about f star. We define the associated string function for f star. Then we take a derivative. In this formula. Everything is on the linear level because nothing depends. You see the coefficient has been frozen, so there's no dependence on the nonlinear flow anymore. The only dependence on the nonlinear flow are given by f star. But f star we already controlled with very good norms. So then it turns out that the difference will satisfy the linear equation with right hand side. I mean, this right hand side is additional to the previous linear analysis. So you have you have this additional term, and but that's the only kind of new thing. And then it turns out that with some work, I mean non-trivial, but still we can do that. The linear flow like this can also be analyzed. In addition, it can be analyzed with respect to the norm that we use for the nonlinear analysis. So basically, H is already controlled. You have this linear flow. Then G can be controlled using H. If you control G, then F is controlled because F star you already controlled. So that in that way we kind of decouple the linear and nonlinear flow. I think I have 1 minute, so let me just okay, let me just skip this. I just mention that in my view, the most important remaining problem at this moment is the nonlinear axiomatization of general vortices. And I think the analysis here will be useful, but there's additional difficulty, which is a degeneracy of mixing at the origin. So somehow at the origin, this transportation, the shearing effect becomes weak. Okay, the derivative is 0 at the origin. So that somehow somehow it requires a different analysis, which we haven't completely understood. That's all for my that's all for that I want to talk about.